right, it's my great pleasure to introduce our next speaker, Jing Xiao, who's Professor and Distinguished Fellow in Robotics Engineering at Worcester Polytechnic Institute in the USA.
Okay, thank you.
Take it away, thank you.
Thank you, Peter. Okay, it is really an honor to present here. I'll try to finish in 10 minutes. So I'll focus on that perception-action synergy is very important, or actually necessary, for fine manipulation skills. By fine manipulation, we mean high-precision arrangements of objects in desired contact states. As Michael just said, assembly is one of the challenges. I first got interested in this problem assembly, inspired by the seminal work from Lozano, Paris, Mason, and Taylor in 1984, and about automatic synthesis of a class of compliant fine motion strategies applicable to assembly tasks. Why? Because assembly tasks are very prone to uncertainties. In this very iconic drawing, you can see that a simple packing hall task can land the pack in different context situations due to motion and sensing uncertainty. So the one key insight from them is that we should plan motion complying to contact that is on the surface of configuration space obstacles, if you have learned configuration space, or C surface, to reduce the dimensionality of uncertainties. We further this idea by consider high-level discrete topological contact formations and automatically generate contact state graphs. So to reduce the problem of planning motion on the surface of C surface as that of planning a sequence of contact state transitions and also contact motion for adjacent contact state to accomplish contact state transition. And this motion plan then is executed online by compliant control using force control. We heard a lot about that recently. But the big problem here is we have a very clear separation of offline, online due to high computation cost. And still, the approach can only apply to rather simple geometry and still subject to uncertainty in contact detection during the actual online execution. And more recently, we see a lot of approaches using deep learning or human demonstration and so on, but with high training costs in terms of data, time, and energy, right? And still, the results are specific to specific tasks and geometry and difficult to generalize. So the problem is, can we have a general or geometry-independent, efficient, and robust solution to real-time, high-precision assembly operations? We started thinking about representation of objects to reduce computation cost. I have done quite a bit of work on haptic rendering of contact situations with my collaborators. We found that sphere tree representation is a higher level representation than polygonal mesh, and has this great property that we can handle all kinds of complex constraints, contact constraints, by simply consider sphere and sphere intersections. But this kind of representation incurs inaccuracies, and there's sensing uncertainty, there's motion uncertainty, we still face uncertainty. So we use learning approach to capture all the uncertainties and inaccuracies, and we automatically collect data to train the relationship between sensing output, force and torque sensing output of 6D vector, right? And contact configuration. So to establish this relationship in a geometry invariant way, because we try to capture the essence of contact interaction and force and torque, rather than the object's own geometry. And that gives us a many-to-many mapping, by the way. So we have to go then back to our object representation to do constraint search under contact constraints to resolve ambiguity to find the best prediction of the contact configuration. The combination of that enables us to do very complex assembly, actually in this case, a 4-packing hall assembly with different shapes of packs, and then we deliberately inject uncertainty into it, so we can have this approach work online actual speed to handle uncertainty 10 times of the task tolerance. And you can see a very close loop of perception and action synergy is here. And this is just to show that this approach is very general. And we apply to gear assembly. And by using vacuum gripper, I try not to handle the complex grasping problem, but we still incur uncertainty between the gripper and the gear picked. But in this assembly, other gears can also move, so you incur even more uncertainty. But this approach works very well. No further training, because the establishment of the force torque sensing information contact configurations is basically geometry free. Geometry invariant, sorry. And we have a paper that I'll present in this afternoon into intersection section. So we further this approach to consider, how about if we use perception to capture the object models directly online? And we just use an RGBD camera, and then objects are totally unknown to the robots. And so we have then consider this tight packing problem of multiple objects. On the left is a puzzle-like situation. We build the puzzle by just randomly draw some curves and cut the objects pieces along the curves to create a puzzle. And on the right are just real-world objects borrowed, purchased from stores with no model whatsoever. So this is all online built with model and very fine packing. Certainly, we also have packing algorithm to decide the sequence of objects to be packed and the location of objects to be packed, and so on, so that all of these perception, model building, thinking, and action. I don't talk about action. Action is slower because we try to make the robot move slower, and you can see all the intricacies of contact. But the thinking part takes only milliseconds. Okay, I have quite a bit of time still. But you can see that this is just to show that we complete the puzzle. Of course, the robot doesn't know it's a puzzle. It's just a bunch of objects and try to pack it. And in the end, the best solution is to finish the puzzle. So we further, recently, another student of mine considered just use perception action to do manipulation beyond pick and place, beyond just grasping, without modeling the object. We pick up a rope, a deformable linear object as an example. And we have an RGBD camera, but actually we only use the RGB part of the camera. So we have no simulation, no object modeling, and the program can apply to different kinds of ropes and even different kinds of fingers. The key here is try to describe the task in terms of the spatial relationship between the finger and the rope, so that with perception, and these are perceptible relationship, and from the perception, the robot tries to reach the desired spatial arrangement, and with corrective motion if necessary, so to achieve this very tight loop of perception and action synergy. And I think that this kind of work really have potential. We can leverage, large language model to describe objects or describe tasks at the object level, and also leverage large visual perception models to help make perception even more powerful. So a lot can be done. It's very interesting, but I think hopeful still. By the way, there's no human demonstration. I'm not against human demonstration. It's just to show that without human demonstration, the robot can also achieve some rather interesting manipulation tasks. That's pretty much the end of my talk.
Well done, Jing. Thank you. Do we have questions? We have time for quite a few questions. Question over here. You'll be next. Yes.
Hello, thank you. Very nice talk.
Name and affiliation, please.
Oh, yeah, my name's Jing. I'm from TU Berlin. So I have read a lot of your nice paper about contact formation, so it's very fantastic to see how we can model contact states. But now the question is, I find it's very hard to associate your contact formations to the demos like what you show. So is now action a part of contact representation, or is there kind of separate?
Yeah, a very good question. I kind of moved away from the very precise geometrical representation of context. As I said, we use just sphere trees, and I don't mind it's inaccurate, but try to capture contact constraints in a unified fashion so that we can actually also relate force torque sensing to this kind of contact situations. So it works better. You can consider a contact is described in terms of spheres intersection, basically.
Thank you.
Thank you. Question in the middle.
Really interesting talk. My question, kind of for all the speakers this morning, is these are all, I believe, with rigid end effectors, and so how much does real-world grasping or in-hand manipulation really depend on some sort of compliance? I think as humans we need that. You talk about compliant control, but I mean physical compliance. And how that would affect this framework.
Yeah, for the videos I show, we use force torque sensing, but I have previous work, we don't use force torque sensing, just use the torque compliant robot. We heard a lot of that. Just from the torque to compute end effector force for that to control. But that's important. Some compliance is important. And I'm not sure about the rope coiling task. And I also did some work with a continuum robot that has natural compliance for whole arm manipulation that can really do a lot more with different types of objects in that sense.
Okay, thank you.
Thank you. Great question. If you want to ask the same question of the previous speakers, see them at the Meet the Speak area. Jing, thank you. Thanks again very much.
Thank you.